let's talk about partial fraction decomposition. Considering this rational function right here, partial fraction decomposition means how can I write this rational function as a sum of two simpler fractions. And in order to be able to do that, I have to be able to factor the denominator of my original function. Okay? And when I do that, I'm going to treat non-repeating linear factors. Okay, in other words, linear factor is of the form x minus a or x plus b, and any of those factors that don't repeat I'm going to treat differently than any linear factors that do repeat. And if I end up with any non-reducible or irreducible quadratic factors, I'm going to treat those differently as well. So for today, or for this part one, let's just consider non-repeating linear factors. Okay, any non-repeating linear factor such as x minus a is going to have a decomposition term of this form here, where I have some number over that factor. So let's take our rational function. First thing I need to do is factor the denominator. Okay, and I can see that I have two non-repeating linear factors. And each of them is going to have a term that looks something like this. So let me rewrite that this way. I have this original function is equal to something like this. I need to find out what a and b are. The first thing I'm going to do is multiply both sides of this equation by this entire denominator here, or in other words, by both of those factors. Okay? And that's what this is right here. This over here is going to serve to eliminate this denominator and give me 5x minus 5 on the left side of the equation. Over here, I need to distribute this multiply into both of these terms. When I distribute it over here, the x plus 1 will cancel with this x plus 1, and I just get a times the quantity x minus 4. When I distribute this over to this term, the x minus 4 will cancel with that x minus 4, and I'm just going to get b times the quantity x plus 1. Distributing the a and the b into their respective quantities, I get this over here. And I can see that in order for this equation to be true, this coefficient here, the 5, has to equal whatever this coefficient is on this side, which would be a plus b. The coefficient of x is a plus b. So I get one equation, 5 equals a plus b. Then I take the constant term here, the negative 5, and make it equal to this constant term. So I get negative 5 equals negative 4a plus b. So I have these two equations. This is a system of two equations in two variables, and I can solve that using matrices. Okay, so here are my two equations in two variables, and I've lined my I've lined up all my variables on top of each other and my constants on the other sides of the equations, and I've got it set up to use a matrix. And I'm going to write this as an augmented matrix now, with all my the coefficients of my variables here and my constants over here. And now, using matrix operations on my calculator, I plug this matrix into my calculator and go to Matrix Math menu and use the reduced row echelon form. I'm going to get this for my result matrix. This tells me that A is equal to 2 and B is equal to 3. So now, going back to my partial fraction decomposition, my original function is equal to 2 over x plus 1 plus 3 over x minus 4. And if I go through and add these fractions back together, finding the common denominator and adding the fractions, I will get this function back again. But this is my sum of two simpler fractions that equals the same thing as the original rational function.